Our third talk today is from Roy Painter from PennDOT. He's going to talk about the SR 4099 emergency slide repair.
Hello, everybody, and welcome. This is the SR 4099 slide repair presentation. I'm Roy Painter from the PennDOT District 12 Geotechnical Unit. The area on the right is a map of the project site location. The area to the south of the circled area is one of the ways in and out of East Vandergrift. The other way is up through this 1,000-foot stretch of roadway that was built on a old landslide material to get into Vandergrift. The area that's south there's a railroad track that crosses at grade along 4099, and on further south, there's some dips in the road that are there due to mining of the Upper Freeport coal seam. If you look at the pictures on the left, the houses there are the last two remaining houses for that 1,000-foot stretch of roadway. There's cracking in the roadway in both lanes. It goes across into both lanes. The northbound is on the left and the southbound is on the right. There's some dipping here on the northbound lane, just in front of this last white house here. And there's also holes, like sinkholes, that develop along the gutter line in the northbound lane between the sidewalk and in the roadway. If this road would be closed, there's a 6-mile-long detour. And as I just mentioned, this would probably be this is the only way in and out for East Vandergrift aside from this other way, so they would be landlocked if something would happen to the southern part of 4099. This was one of the first projects that was fully administered during the COVID-19. From March, we had a Skype meeting, scoping field Skype meeting, and there was no let, but there was emergency procurement proclaimed on March 13th. This is just a perspective of where it's at in the state with relationship to all the districts, PennDOT districts. It's bordering District 10. It's up in the northwest part of Westmoreland County, and it's in the southwest part of Pennsylvania. Here are comparative photos from 1974 and practically today. Nothing's changed from these photos, really, on the right. And as you can see, there's houses lining the roadway left and right from the same picture that we have from today. Note this White House because we'll be talking about it later in a couple of slides here. Here's that White House. And Frank Jones was the district geotechnical engineer at the time. He had the opportunity to go and visit with the people that owned the house and write a letter afterwards explaining that it's not PennDOT's fault. It's the slopes around the road that are causing the problem. Here's a picture from the outside of the White House. And the utility pole, a little bit down further from where the White House would have been in the slope. This pole, when they put the sidewalk in, this pole was actually formed into the sidewalk when they built the sidewalk. Pole number 1. And as you can see, the slope has moved about 1.5 feet from when they put the sidewalk in. The pole is moved, and of course the pole moves with the slope. There are 3 structures that were removed in the 14 years between December 2005 in 2019. They were all on the right-hand side, circled and pictured here. And you can see there's GH holes painted on the roadway here. Those are grout holes, and we grouted under the roadway at that time because there were 5 to 8 foot voids discovered just underneath the brick of the roadway structure throughout this area here in this northbound lane. So we grouted them up in 2005. This wall was bowing around the same time we put the inclinometer in, inclinometer F9. And in March, just before we determined this was an emergency, or around the same time this wall collapsed, a little bit of history more here. June 2017, we did a repair. We went down 8 feet, about 2 foot, like a bucket foot wide. And as far as we could go in the area that was having trouble where we saw sinkholes, we excavated out and replaced it. Some areas, like you can see in the foreground of this picture, there's concrete that was already there, so we didn't remove it. It was hard to excavate that area. So we left that in place, probably from previous repairs that they've done. Similar to what we just did. That was only about 100 foot long repair that we did there. Here's some photos, a series of photos that show from both Google Earth and Penn Pilot, historical photos, the history of the disappearing of structures along this stretch of roadway. This picture here is pretty much what you see now. Hasn't changed since 2014. I count 4 structures along this hillside. Those 2 are still there that we saw at the beginning of this presentation. I circled them, and there's a couple foundations here you can see. Way back, 1957 here, I counted 17 structures. I think I got them all. I tried to count them all here. You can see both sides of the road had structures, and some of those we had pictures of early on in the presentation. 1993, there's still one remaining over here, and there's a couple here. Here is the soil slide prone map from the USDA Web Soil Survey, available for anybody to access for the whole nation to see. And there's a lot of good information available in that at your fingertips. Soil scientists developed, put together all kinds of good information, and they have it available for anybody to access. I'll show you at the end, near the end, how to access that and produce your own maps. Usually if it's slide prone, it's red or yellow. In this case, it's definitely slide prone, it's red. And yellow, we do see a lot of problems with yellow soils too. The consultant that we had to help us in our design found an old map that traced even more precisely, perhaps, where the slide prone soils are. And the ERC here is about where that White House is. And you can see where we did that 8 foot deep trench right here where it's orange. And it shows the borings that we drilled at that time in 2017. They're F-series borings. F9 and F11 were the 2 inclinometers we installed. Here they are, a little close-up shot. And you can see that line comes right through at the edge of that porch, right near that front yard. And you'll see later we saw cracking just right there too while they're doing this construction. These yellow dots represent the 322 pipe dowels that they're installing for the slide repair. This just shows you about where the inclinometers are with relationship to everything. So F9 is further away, F11 is closest to the house. And here's a picture of them in the field off just over the slope here. And F9 definitely showed an increase in movement, 10 times the increase in movement during construction than it did previous to construction. F11 was unreadable as of February of 2020 because it had so much movement. I guess it pinched off or pulled apart. We couldn't read it anymore. Here's the conceptual design that we're putting in the repair. 2 rows of pipe dowels. You can see they're staggered, which activates soil arching to help fix, to stabilize the landslide. And we're going to tie them together with concrete at the top. And we're going to detail basically what we did to come up with the design for the pipe dowel system. So we drill borings, and in the borings, we put these inclinometers, and we got to see where the sliding was occurring. In this case, in F9, it was occurring in the weathered bedrock zone. Here's the readings. The axis AA is down over the slope direction. BB is with traffic direction. And you can tell that the movement before the construction was pretty consistent, 0.5 inches per year approximately if you compute it out. And then once construction was getting going, it increased 10 times. F11, that shows sliding right on bedrock beneath the weathered rock zone. And it also shows the definite movement area. There's consistent movement here. We did some soil testing on those F series of borings too. Got laboratory test results back for those. We used as much as we could in our analysis. We did back analysis also to help figure out our soil parameters and fit the failure surface right through where we saw the movement in the inclinometers. Adjusted the friction angles to make sure we got a factor safety of 1, which means it's failing. Then we gathered the forces up at the point where we would put the pipe dowels. We'd use that to help develop what landslide forces we need to resist. Put the piles in and get a factor safety of 1.86. Did the same thing at another section too. Same process. Back calculate friction angles to get a factor safety of 1. Get our forces, and then we get a good repair, 2.1 factor of safety. We're going to check the deflections. At the top, the tops aren't connected, so we have large deflections, 20 inches of deflection for 1 POW. Moment of inertia is in the 30s, 37. Connect them up, 100 times more moment of inertia, and you get a lot less deflection, acceptable deflection. Hand calculations for the moment of inertia in the 30s for 1 POW, and for group effect, 100 times more moment of inertia. Here's what the contractor's building right now. 80 KSI steel, 10 foot. We always socket these 10 foot into the bedrock. And we're tying it together at the top with that concrete of the sidewalk at the top. Here's some notes that the contractor's using in the construction to make sure that they get everything right. Grouting from the bottom up, vibrate them, make sure the concrete's going around them really well. Here's some pictures from the site. We were called out to look at some of the cracking, like I mentioned, that was occurring right here in the front yard. Pretty much right in line with that line that the consultant found with the slide mapping. And being that these are unreinforced, we could expect some movement to occur. Here's a picture looking south. Contractor's on the right, consultant that helped us design it is on the left. Here's another picture looking north. They're doing a good job. They're pretty much done it with all the piles they need to put in. They were just had a few more left up there. Here's a picture of the last remaining house. The cracking's right through here. Here's a picture of the cracks. And here's some takeaways from the presentation. Everybody can access this information through the web soil survey. Here's the step-by-step process on how to do it. And you can create a colorful map to know whether or not what you're building will stand or not, and you need to stabilize it before you go any further or whatnot. And some other takeaways. We saw slope movements that were consistent through the years, and when we started construction, they sped up quite a bit. And once you connect the tops up, you reduce your deflections considerably. Okay, thank you. If there's any questions, please call me, 724-439-7357, or email me, ropainter@pa.gov. Thank you for your time, and I wish you well with your studies and your life, and hope you learn all you can in school, and hope to see you soon. Thank you.
All right, so that was Roy's presentation. I'm glad, even though he wasn't able to join us today, he was able to get it recorded and able to have us see it. So just one quick question maybe. And I know he's not on here, but I know Joe Shazer and Pat Brown, who are intimately familiar with the work, are on the call as well. Could you please give a brief description on what an inclinometer is and how it functions, since a lot of us on here may not know that?
This is Pat Brown.
We can hear you, Pat. Yep.
Okay. Yes, it's basically drilling a hole. These were drilled down into rock, and then you insert inclinometer casing. It's roughly a 2-inch diameter casing or so. You grout that into the rock and the soil, and then you run an instrumentation down it. It has 4 grooves in it at 90-degree angles to each other. And you run the instrumentation down it, and it reads in one direction, like going perpendicular to the slope, and then you turn it and read it the other direction, you get it parallel to the slope. And so you install that, you run the instrumentation down, and it gives you a baseline. And then you go back periodically and continue to get readings, and it'll show you any movement within that plastic pipe, which is being moved by the soil, the slope itself. And then you can get, whenever you go back, you continue to get whatever rate of movement and how much movement is occurring over time. They're good instrumentations for monitoring any sliding material, other than, like Sebastian mentioned, that if it is moving at a fast rate, then they will not, they'll pinch off, and you'll not be able to get readings after some period of time, depending on how fast the slope is moving.